Is any because we just went over those before, right? Let's just stick to they're the same. Actually, there's actually something about this that would be weird, no? Right, Akash? Because if they're the same, isn't there something fishy about this? Like, are we catching on to? You don't know? Okay. The thing is that ionic compounds don't use prefix. Yeah, exactly. Yes, hard. Yes, you don't use prefixes in ionic compounds. Like, I put that there just to see if anyone would say like, oh, you don't use prefixes. Like, there are no prefixes in ionic compounds. It's only molecular, so you don't have to worry about like putting like mono or di or tri. Like, you don't need it. Like, it's not there. And then why is that? Why don't we use prefixes? Because Jorge said, like, you don't use them, right? So why don't we use prefixes? Why is that? Because we use it molecular, why can't we just use it for ionic? That's for transition metals. Transition metals, you can... Yeah, that's for transition metals. I'm talking about just regular ionic compounds. Does anyone know? If you don't know, it's okay. Like, why you don't use prefixes for just regular ionic compounds. I mean, you don't use prefixes for transition either. Do we not know? You can just write, I don't know, it's okay. You don't know? Okay. It's because the atom's neutral. There's one positive, one negative. They're fine. Like, they're together. It's neutral. It cancels out. Versus two nonmetals are different. So they have like some type of weird charge going on, which is why I use the prefix. Ionic, because one's positive, one's negative. It's neutral. You don't need a prefix. That's it. That's the reason why. Are we good on that? It's like that? Yes. For ionic, you never use prefixes. Neutral? That's what your textbook says. That's what I would use for it, like why you don't use prefixes. I wouldn't say, like, you don't have to dwell on that. Like, if you don't, they're not going to ask you, like, oh, why do you need to know? Like, you're going to be fine. Do you have any questions? This one's pretty simple, pretty easy, I think, right? Ionic? Yes, okay. I'm just going to keep going then. Yeah, but that's the answer. There's no prefixes. Don't use it. You're just going to get it wrong. So yeah, they're electrically neutral. And then, yeah, just the name. The first one is just the cation. The cation always goes first. And then the second one always has "ide." Again, pretty simple, pretty easy, not much to be done. And then, so now we're going to do ionic transition metals. So how do you recognize it? I think I meant how you said it before. So how do you recognize an ionic? This is iconic, but ionic transition metal. How do we know? How do we know that's a transition metal compound? Like, when you look at it, how would you know immediately, oh, that's in the middle of the periodic table? Like, what is associated with it? Do we know? Roman numerals, yes, exactly. And we all know how to read Roman numerals, right? Like, we all know what it looks like. Yes, I'd imagine. So, how do you name ionic transition metals? I mean, compounds. How do we do that? What's the first thing? There isn't really like too much of a method to it. Like, especially in your textbook, it doesn't tell you. But there's like things you can do. There's steps that I think you should do, and it'll get you the right answer. So what's the first thing you do? Like, if you have, for example, you have like copper, right? You have like 2 oxide. Like, what was the first thing you would do? Or you have like Cu. Like, how would you know that? Because copper is a transition metal, right? What's the first step you would take? Does anyone know? Like, what's the first thing you do? Charge of the metal. Yes. So I want to say, well, kind of, yes. Because copper, when you look on this like periodic table, does it show you like what charges are with transition metals? Yes or no? No, exactly, right? So how would you find the charge of the metal? It shows you the Roman numeral is the charge of the copper. Like, anytime you see that, that's how you know the charge of the copper. The charge of the copper is 2. That's how you know that that's 2. So, because it doesn't show you, but on the formula, like, if you see the Roman numeral, you know that's with copper. It never goes to the second element, ever. It's always the first one. So that's how you know that one's 2. And then oxygen is how many, what's the charge of oxygen? Yeah, exactly. So when you cross them, you just cross them, right? Because they're both 2, it just cancels out. So it just becomes CuO. That's it. That's how you know. The only takeaway I want you to get from this is that the Roman numeral is associated with that transition metal. It's the charge of that transition metal. That's how you know. And then you cross it. So once you get that, you cross that and then the other one, which is usually like a non-metal or a metal. So you have the charge of the second element and then you just cross them. Same thing with cross multiplying anything, like you just cross it. And then always simplify it too, because it would just be 2, 2, which you don't want. So you just simplify it to CuO. Are we good on that? No confusion? Because this one's probably the hardest to name, but it's not too bad, I think. So I'm just going to say, okay. So once we get that, what's a polyatomic ion? Do we know? It's pretty simple, I think. Don't be shy. I see some of you guys like almost every single time. You guys are still so shy. Well, yes, exactly. Again, pretty simple. So let's name the polyatomic ions. These are common ones that I would suggest memorizing because you're going to use it not only now, but you're going to use it for exam 4 when you're calculating like formal charge, oxidation number, and solubility rules. So you're going to need this. Ammonium ions. What's that look like? Yes, exactly. So that's NH, and then it's positive. I'm just going to give that one to you. And then acetate. This one's really long, but you're gonna, sometimes teachers put it in equations because it looks really big, so they want to confuse you, but it's really not that bad. Acetate, do we know what that is? If you don't know, it's okay. But I would suggest memorizing it because you're gonna see it again. And it's also like the second rule of your solubility rules, so you're gonna need it anyway. Acetate. If you don't know, you can just write, I don't know. Yeah, yes, it's right. Yes, Eden. Exactly. And then what about chlorate? Do we know what that is? Chlorate goes with chlorine. Do you know what that is? Chlor. Actually, Akash, you're thinking about carbonate. CO3, 2 to the negative, that's carbonate. T is right. It's Cl, which is the chlorine, oxygen, and then 3 with the negative up there. What about nitrate? Nitrate and then nitrate are used pretty similarly, so I wouldn't suggest like mixing it up. Nitrate. So we know there's N in there, right? What goes next? Yes, exactly. That's correct. 2, and the charge, make sure you guys know the charge on top. Like it's positive, negative, because you need that when you're calculating valence electrons. And I'm pretty sure Dr. Kelly's going to put it on your test. By the way, I'm also having a major test review the day before your test. And what I'm planning to do is I'm going to look at your test as per usual. And I'm going to look at what concepts you guys go over, difficult questions I think would trip you guys up. And then I'm going to make a study session based off of those questions that I see. So I would highly suggest going to that because it's probably your best bet of what would be on the test specifically. So yeah, test cumulative. Yes, yeah, because exam 4, you're gonna have to know stuff from exam 2. So yeah, like, and I imagine exam 2, you're probably not gonna need exam 1 very much, but like when you get to exam 4, you need to know exam 2 specifically. Like how to do ion. Like when I went to exam 4, I was like, oh my god, I don't know how to do this, and I realized I forgot it because it was like 2 months ago. So you have to know it. And then hydroxide. This one's pretty easy. What's hydroxide? Yes, exactly. You're also going to know that because it's also part of your solubility rules, which I have a chart for, and I'll print it out, or I'll send it to you guys when it's time. I also have a practice test coming, and an exam 2 guide as well, so I'm trying to send it to you guys maybe like a week before your test, or a little, like maybe like Monday or Tuesday. So phosphate, what's phosphate? Is phosphate. Yes, PO4, exactly. And then do we know the charge on top? Because that's pretty important too. Because it's PO4, right? Yes, 3. It's actually 3. 3. And so what about sulfate? Do you know what sulfate is? I'm gonna give you guys time to type it out because I know it's pretty difficult to like do it really fast. Yes. SO4. Yes, exactly. SO4. And then the top one is actually 2 chloride. So again, like you have to know like what it is, the negative, positives, and all that stuff. I think let me look here. I think I have a chart for this. Yeah, you guys are gonna need this, by the way, and I'll send a photo of that because I used it during my test and it really helped me. I also have another equation sheet, so I'm gonna send that to you guys at some point as well. And then common polyatomic ions. So again, I'm not saying you should memorize every single bit, but like there's definitely a lot you need to know. So yeah, do we have any questions on this? Again, this part is just like memorization on the polyatomic ion side. Yes, are we good? I'm gonna say that we're good. Okay. Okay, so that's how you do it. Do you have any questions? Yes. And remember, carbonate is CO3. Chlorate is ClO3. Are we good? Yes. Okay. Okay, this is a study sheet, and I would suggest knowing these. This is from your textbook, but common like naming prefixes, common polyatomic ions. This is like in your textbook, so if she's gonna take out polyatomic ions, I imagine it's probably gonna be from this. Like, so know this. I don't think some of these are that important, but the ones I just listed are very common ones that when I took Gen Chem 1, I used all the time. So yeah, you study that. And then practice problems. Okay, let's just get into it. Dichloride tetraoxide. What's the chemical formula for that? This one's pretty easy, right? Because it's just a molecular compound. Okay, and what does everyone else think as well? Okay. Any other takers? Do we all agree with this? Disagree? Okay, so you are correct, but you have to simplify it. Because on the test, they don't write Cl2O4, they just say ClO2. You have to simplify it. Yeah, so I'm just going to write that out. Cl2O4 goes down to just ClO2. Yeah, because they always use a simplified. They don't do Cl2O4. They just say ClO2. What about aluminum bromide? Aluminum. Okay, very good. Do we agree, disagree? Very nice, yes. And again, you just cross it, which is why it's AlBr3. Exactly, lead oxide. What's that? And that's a transition model, right? So we don't know exactly the charge for lead. So how would we do that? Where does 3 come from? Yeah, aluminum 3, you're looking at the charges on the periodic table. That's where that comes from. PbO2, do we have any other takers? So we know oxygen's -2, right? Do we agree with the Kosh, or do we think, oh, that's wrong, I think it's this? Because we went over how to do this, right? Agree? Okay, does anyone else agree, disagree? Is this our final answer? Yes, no, see, okay, yes, you're correct. And that's because this is 4, and then you cross it, simplify, you get PbO2, perfect. And then iron carbonate. In carbonate, I never went over with you guys, but someone listed it before. I think it was Jorge, and we talked about it. So, what's that one? What's carbonate look like? Do we know? If you don't know, it's okay. Okay, we have some answers. Do we all agree, disagree? Yes? So this is, by the way, this is carbonate, just in case you're like, what's carbonate? That's carbonate. And then iron, we have 2, right? So you cross it, it's going to be just FeCO3. So T is correct. Do we all understand how she got that? Yes, okay, perfect. Nitrogen gas. What's the chemical formula for nitrogen gas? N2. Yes. Did we agree, disagree, confusion? Yes, no. Okay, I'm just gonna say, like, if you agree, just raise your hand. So that's how I know if you agree or not. Okay, exactly. Okay. Actually, I'm gonna go over that, Akash. And the reason is does anyone know why it's N2 and not just N? Like, what's the reasoning behind that? If you don't know, you can raise your hand. Diatomic. Yes, it's diatomic, and there's 7 diatomic molecules just like that. And Akash, it does include oxygen and nitrogen. I think iodine. What else? Nitrogen stuff. Again, like stuff like that. And when it's diatomic, it's more content being with another molecule of itself, which is why it's like O2 N2. So what about mono? I think this supposed to say chlorine oxide. What's the chemical formula for monochlorine oxide? Do we know? Yes, no, I don't know. O2, okay. Does anyone have anything else? Do we all agree with that? If you agree, you can raise your hand. Yes, so we all agree on that? Exactly, yes. So Natalie, you're correct. Exactly. I did that to trick you. Monochlorine oxide doesn't exist. That's not a thing. That will never exist because it starts. I'm tricked. Exactly. Yes, that was my intention, and it worked. Yes. Okay, but mono again, like that's why I said exception. You can never have it. And yes, Natalia and Jorge, you're completely correct. That would never even work. So what about Cl2? So we know that's copper. We know that's chlorine. How would we do that? Copper over here, chlorine. So what's the form? What would be the name for this? So we're working backwards almost. So what's the first thing we would do? Or what's the formula? I mean the name for this. Copper 2 chloride. Okay, do we agree, disagree? Yes, exactly, yes. Because it goes on here and 2 is over here because there's nothing on this side. That means this one has to be 2, which means it has to be copper 2 chloride. Okay, very nice. What about copper ClO3 2? And we know this as being chlorate, right? Because we just went over the polyatomic ions. So again, this is transition metals with polyatomic ions. 2 chlorate. Do we agree? Disagree? Yes? No? I don't know. Yes, exactly. That's correct. Does anyone have any questions on that? I think it's very similar to this one above. So I think we don't need to work on it too much, right? We're all good? Okay, what about helium or HeO2? What would that be? Do we know? Because that's helium, that's oxygen. So when we do naming, what is that going to be? Helium dioxide. Okay, do we agree or disagree with that? Those bond. I don't know, Akash, do they? Actually, the answer would be helium oxide. And I know you're like, oh, that doesn't make sense because it's like it wouldn't work. And that's the thing, it doesn't really work, which is weird, but I don't know why, it just is. You probably won't have an example like this, but it's actually 2 goes with the prefix and non-Roman numeral. What example are you talking about when you say that? By the way, helium, it's just helium oxide. I know it's confusing because it's like, oh, there's a 2 right there, but there are exceptions to certain rules, and that's an example of like one of the things. Transition goes to the prefix. Yeah, the 2, like you would know this is 2 because it goes to this. Like ionic compounds, they don't even have prefixes, so you don't have to worry about that. We're good on that. We're okay. think we're okay. Okay, what about the next one? PB2. What is that? Do we know what that is? Because this is lead, right? How do we know what that is? Does anyone have an answer? This one's kind of tricky, I think. Do we know? If you don't know, it's okay. You can just put out some answers. It's okay if you're wrong, too, because I'd rather you be wrong here than anywhere else. Okay, so someone said PB2. I don't know. Okay, so we're also confused, right? Are other people? Raise your hand if you're confused. Okay, exactly. Yeah. Okay, so I'm just gonna say that this doesn't exist. This is also a trick question that I put there just to confuse people. Because I like to confuse you guys because I hate everyone. That's a joke, by the way. I don't hate any of you. I love all of you. But anyways, PB2 doesn't even exist. Does anyone know what PB2 even is? Like, it's not even an element. It's not really a compound. It's actually pressed peanut butter. It just looks like it'd be lead, but it's actually just pressed peanut butter. I found that one time in an article, so I put it in here, because I thought I'd confuse you, and it did. So, good. Nice. Do we have any other questions? Yeah. Do we have any other questions? Good. Okay. If you have a question, you just talk through your mic, if anything. Okay, you can put your hands down. You're done. Okay. So I'm going to keep going. Yep, it's just peanut butter. And then here are the rest of them. They press it down to like a powder. You can put it in water and like drink it. It's pretty cool. I saw it in Kroger once. Anywho. Oh, I want it. I should buy some. Anywho. Do we have any other questions? T, are you okay? Your hand's still up? Are we good? Okay, good. Perfect. So we're doing Lewis structure symbols. What's the octet rule? This one's pretty simple. How you draw like Bohr models, Lewis structures. What's the rule? What's the structure it goes into? Anything else? Okay, is it for every single one? You need 8 electrons? Are you sure? Do we have any other takers? There's exceptions? There's specific there's a specific rule that says everything you guys are saying right now. Outer than inner? No, okay. You can have okay, I'm just gonna write it down. It's 288. The first ring has only 2, and the rest of them have 8. That's it, it's just 288. That's what I'm talking about when you guys say, oh, there's exceptions, not hydrogen. Yeah, exactly, because it only needs 2. That's the point of the 2 right here. It's 288. And then let's go to the next one. Elements in the same group have what? In the same what? Elements in the same group. So we have the periodic table. This is group 17. Valence electrons. Yes, Natalie, you're correct. And what about the same what? They have the same valence electrons and they have the same what? Charge. Yes, and what? This one's pretty simple. And it's supposed to help you when you're writing your Lewis structures. But Jocelyn, you're right too. Yes, it's the charge and the valence as well. Bonding order. Yes, here, I'm just gonna write it. It's the same dots. Like, if you're in the same group, you're gonna have the same dots for each element because you have the same valence electrons. That's how they connect. Bonding order, you're gonna need that later on, and I'll show you in a little bit. But so hold on to that for it. And then how do you find valence electrons? I think I just said it. What? Can someone just re-say it really fast? How do you group? Exactly, yep. And then just like group 17 is gonna be how many valence electrons? For example, 7. Yes, exactly. So if an element has a positive, what happens to the overall valence electron score? It's supposed to be an E right there. Electron. Okay, and what about negative? Like if you have like Ca plus 2, or you have like N negative, like what do? How does that affect the valence electron? Yes, exactly. So positive, you subtract whatever number's there, and if it's a negative, you add it to the valence electron. And then when you draw your Lewis structure, it should equal exactly the same amount. And if it doesn't, and like let's just say like, oh, you don't have enough, but it's not enough to create a lone pair. Like you don't have, for example, if you have one left over, and you can't do a lone pair, right? Because you need two to do a pair. So what do? Does anyone know? Like for example, we have F, right? And it's like bonded to like N and like O. And what happens if it's all filled, but you have like one valence electron left? You can't make a pair, right, on the central N because you need a pair. You need two. So what do you do without one electron left? What do you do? How do you signify it? Does anyone know? Like, what would you do? Yes, exactly. You would put it on the side, yes. And then Natalie, yeah, it's what Eden said. You would put it on the side. So when you have your brackets, that's a terrible photo, but like, you would have your brackets and then you can put negative there. You can have your brackets and you can put positive. And that's how they would know you're talking about one electron because you don't have enough to put it in a lone pair on the central. And then when drawing Lewis structures, why do valence electrons matter? Like, what do they matter? We already went over this, I think. It's pretty simple. So drawing Lewis structures. Yeah. Bonding ability. I think you guys are thinking about it very complex. Like, it's pretty much just how many dots you're going to draw. Like, how many lines, how many dots. And we all know that the structure is 2 per one, right? So you have 2 dots here, 2 dots here, 2 dots here. So we all know how that works, right? Yeah, but valence electrons is just to calculate how many dots or like lines you're gonna need. Are we good? Yes? If you understand, raise your hand. Okay, yes, okay, thank you. Okay, so that's the rules. The colors are very stark, I like them. Okay, next one. How do you know when to use a double or a triple bond? For example, you have C2, this is C3. How would you know when to use it? Or when do you use these? How do we know? Oh, we should use a triple bond, double bond. How do we know it's time to use a bond like that? When you're doing a Lewis structure, right? Because we don't always use single bonds, especially when you're using carbon and oxygen or carbon to carbon. There's always like double, triple bonds sometimes. So how would we know? Yes, that's a part of it. Yes. So when you put it all together, if you have, for example, like, okay, so double, triple bonds. So let's just say you have too many valence, so like you filled up all your valence electrons. Let's say you have this, right? And it's equal to like C, so you have like CCO or something. And let's say you used up all your valence electrons on the side. Like you're done. You don't have any more. You only have like, for example, like 12. You used all 12. What do? Because this doesn't have an octet yet, right? C's not filled. Like if this has 6 on the outside and this also has 6, C's the only one that's not filled, but you can't put more lone pairs on it because you can't. There's not enough valence electrons. So you will put this on there. You do a double bond, or sometimes, usually triple bonds exist between 2 molecules, but that's how you would know. You run out of valence electrons, you need an octet. That's it. That's super simple, super easy. So next one. How do you know the order of the molecules when drawing Lewis structures? What trend? And I think Stephanie asked me about this like a few minutes ago too. So what about this? How would you know the order of the molecules when drawing Lewis structures? What's the trend? And by the way, there's an exception to this trend as well. So for example, you have like let's say you have C, S, O, how would you know? Okay, less to more electrons. Okay, actually, Eden, Akash, and Natalie are correct. It's the more electronegatives go on the outside, the least electronegative go on the inside. And if you have one that equals it, you just have to like figure it out. Like there's no real like answer I could give you. Like for example, I think C and like another atom like Cl, like they're equal or something in electronegativity. You just have to like figure it out. Usually C's in the middle, or you could also say if there's like CH Cl3, which one would be the the central atom. How would you know? Out of CHCl3, C. And how do we know that? Because I think hydrogen and chlorine have the exact same electronegativity, right? So how would you know? Yes. And yes, H only bonds one. H is rarely ever central atom. It's almost pretty much never. It's kind of just there. You can only do one single bond. H is only two. Like, we all know that. It's only one single bond. It will never go over. It will never change. Single, always, forever. Like me. So when you have carbon, yeah, it's usually going to be in the middle. So what do you do if there are more valence electrons than the number of molecules present? What do you do? Right? Because if you have like N, O, N or something, and you have more valence electrons than the number that's present, and all these are full, like there's 6 on here, there's 2, there's some charges. You would do that more if there were 1, or if you have like an uneven number like 3, you would use it. Well, what's something fast you could do? Like if there's 4 on the end, 4 on the other end, and then 8, so it fills octet, but you have like 2 more valence electrons, what would you do? You're close, Eden. But what's the thing you do? You eat them? Yeah. Actually, you said it before. It's the lone pairs. I find it ironic that you missed the one above there with lone pairs. No, you got that one, but then you missed this one. It's very weird. But yeah, you just do lone pairs. You have 2. Yeah. Okay. But do we all understand that? If you have an excess of valence electrons, you can just, and they're like an even number, like 4, you can have like 2 lone pairs. So are we good on that? Do we understand? Yes, perfect. Okay. Yes. So those are the answers. Look at the bright colors. Have fun with that. I really enjoy putting colors in these PowerPoints. Okay. Practice problems. Okay, draw calcium fluoride with brackets. How do we do that? And I'm just going to give you the chemical formula because I know it's kind of difficult to see or to understand because it's ionic here. So CaF2. How would we draw that? And you're using brackets, so I don't want to see like bonds. I want to see like the bracket versions of this because it's only ever done in brackets. How would we do this? Here, I'll even draw it out. You can tell me what to do. You can teach it to me. So what do we do? What's the first thing? Do you know? What's the first thing you look at? You're looking at the periodic table, you have calcium and fluorine. Like, what do you do? Group number, yes, you're using the group number to find what? You're using group number to find what? The valence electrons, yes. Okay. So, F has how many? F has 7, exactly, 7. So you have 7 on the sides, right? So what do you do with Ca? What do we know about Ca? What's the charge on Ca? Just wondering. 2, right? Exactly, it's plus 2. So fluorine has 7, right? So it's itching to get 1 more. It needs 1 more, right? So it's highly reactive and it wants that 1 more chance. And Ca just happens to have 2. And why? When you look at that, there's 2 fluorines. So what are we going to do? What are we going to do now that we have this information? Single bonds. There's a different answer to that. There's no bonding in this one. This one only has brackets. So what would you do? Because you know Ca has plus 2, right? And you have 2 fluorines that need 1 more each. What are you going to do? What are you going to do with that Ca? You're going to... There's 2. Need 2 on for each one. Or 1 for each one. What would you do? Do we know? Donate them to full. Yes, exactly. So you're going to put 1 more here, and look, it makes it full, so now it's perfect. So once you do that, you would put, and because it gained 1, what would you put up here? Negative, yes, exactly. So that's how you would draw that, negative. And then because CH2 is just going to be plus 2, that's how you do that one. And then, are we good on that one? Because now we're going to move to CHCl3, which is very similar to the one we just had before this. So we know C is the middle, right? You have H going up here, Cl. So what do we do first? How many, what are we using for Cl? Group number, right? How many are in Cl? 7, exactly. So you have 7 on each side. So what's going to be the full valence electron? Like, what's the full answer? How many valence electrons are we going to have in this? 27? Are you sure? Do we agree? Because 7, right? 7 times 3 is 21. 30. Jesus. No, not 32. Here, let's just do it together. 7 times 3 is 21. So that's going to equal the Cl aspect, right? And then C has how many? How many does C have? 4. Plus 4, what about hydrogen? 1. And when you add that together, what do you get? You're adding them. So 21 plus 4 plus 1 is 21 plus 5, which is 26. Yes. There we go. That's how we add. Yes. So how do we get 4? You're looking at the group number. Carbon is in group 14, right? So you're going to have 4. That's how you get 4. So that's how you find the full valence electrons. Use this every single time you have to draw it out. Every single time. That's how you know you're doing it right. So you don't get like 27 or 32. I'm pretty sure Akash just calculated wrong on accident. But when you do that, 32 is not correct, no. It's 26. So once you do that and you count it all out, you get 8, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and then 26 is the last one. So that's how you know. That's kind of confusing. Yes, no, are we confused? No? Okay. So what about an ammonium ion? Because we know it's just NH4, right? But it has a charge on it. So we'd have N. And then what else do we do? All single bonds. Yes, exactly. And then do you put anything on the outside of the brackets? Yes, no? Because when you do that, how many group number or like the group valence numbers are in nitrogen? Let me ask you that. Because we know H is 1, right? There's 4 H's, so that's 4 plus how many are in nitrogen? Nitrogen is in group 15, so we're gonna have 5, yes. And that's 9. But the thing is that there's a positive, which means you subtract 1, right? So you have 10, you have to subtract 1 now, so it's gonna be 9. But you don't, that's an odd number, you can't do that, right? So you have 2, 4, 6, 8. You have to do a plus 1 up here to show that you have 9. Are we good? I'm gonna assume we're good on that. It's pretty simple, I think. What about OH? How do we do that? How many, what's the group number for oxygen? Like, what's the valence electron? 16, right? So what's that gonna be? 6, exactly. 6 plus, how many for oxygen? Oxygen is in group, which means it's gonna have, well, actually, no, that's hydrogen. Hydrogen has what? How many? Yes, 1, exactly. So that's gonna be 7, right? But look, there's a negative right there, so you're going to do what? Yes, you're gonna add 1. Yeah, negative 1 is just the charge on it, but you have to add 1, yep, so it's gonna be 8. So when we do that, we're adding, because hydrogen can only have one charge on that, right? There's no valence electrons that will ever go on there. So you would just draw the little dots on the O. Bracket, of course. And because this is like one of those atoms where it's like a polyatomic, usually you're gonna put like that little sign right there. Are we good on that? Okay. C2H2. How do we do that? You know, H goes on the outside, no? Because C, again, like what Natalie said, it's gonna have priority as being essential. So you have C, C, H. What do you do? How many valence electrons are gonna be in this fully? Because we know what C is, we know what H is. What is that gonna be? Just add it. 10 exactly, yes. So how do we get 10 from here? What do we do? Hydrogen can only have a single bond, right? So what happens is C and C. How do we get 10? Because right now we only have... See, you could do that, but you can't. The problem is there's not an octet, so you add in lone pairs. There's a more efficient way of doing it. Like you wouldn't have to use lone pairs. You would use something else. You would need the octet to do something else. Triple bond. Yes, exactly. Triple bonds. Very good. So that's 2, 4, 6, 8, 10. Yes, in lone pairs, you would only use if it already has an octet, and then you would use the lone pairs. That's how you know, Akash. Only for octets that are already full. So we're good on that, I imagine. There's no like single electrons on this one. So what about phosphorus trichloride? So there's gonna be one phosphorus. What about chloride? How many chlorides are we gonna have? Do we know? Because there's a 3 exactly, yes. So 3, 3, 3. So how many valence electrons is in this molecule? What's the full number? Because we know Cl is how many? It's 7, right? And there's 3 of them, so that's 21. 21 plus how many are in phosphorus? 26. Yes, that's correct. And you would add 5 to that. So yes, Akash and Eden, you're both correct. That's 26. So when you do that out, you will get 7 on, you get 8, right, on chlorine because you're trying to fill those up. Here, I'm just going to do it like that so you know it's 8. So these are all full. All the chlorines have 8. What about phosphorus? Because right now we're at 24, but this is also not full, so what would you do to make it not 10? Because lone pairs can also be used this way as well. So what would we do here? What would we add to know? What would be added on top of phosphorus? One lone pair exactly. And by the way, that noise is like me cracking my knuckles. I love doing that, by the way. You'll hear it periodically. But yep, that's how you do it. Any confusion? We're all good? We're all okay? You raise your hand if you're okay, like you understand. Okay, nice. Okay, so this is the actual stuff. I got this from my textbook too. So again, like I think it does a pretty good job. It goes over like polyatomic ions, molecular, ionic. So again, not too bad, I think. The only thing you would have to practice is transition metal ones. Okay, but next, blast from the past. This one I really want you to pay attention because you guys have a quiz tomorrow, right? Yes? I think someone said, yeah, you guys have a quiz tomorrow. So I would highly suggest paying attention to this and just knowing it, just because who knows when stuff may pop up, right? So yeah, if I want you to get anything from this, look at this slide and know it for sure. How do you determine bond order? What would you do? Or how do you know? Bond order. So you have like C or like S. What's the bond order of this? How do we know? This one's pretty easy. How do you determine bond order? The bonds. Do we know? If you don't know, you can just write, I don't know. Yes, no, I don't know. You can just write, I don't know. If there's no like silence, I can just assume. Okay, bond order for this, you're just gonna count this as each single bond, so that's 3. The bond order of this is 3. That's it. That's pretty much it. What about bond energy? Because we have bond order, right? What's the bond energy? Bond energy. Bond order. Bond order, you're just, again, like, it's just, you're just looking at between the atomic ions, like how many bonds there are. So for this one, we have 3. So that's how you would determine. For this one specifically, that you would use in the near future, I would suggest just counting that. And then bond energies, how would you find bond energies? Yes, but how would you know looking at this? If you don't know, I can just tell you, it's okay. Bond energies is how many there are? Well, that's bond order for this. Okay. So bond energy for this is going to be the stronger bond energies have more lines. It's just, yeah, I'm not doing numerically, I'm just doing the trend. So the more lines you have, the stronger that bond is. And then what about the length of the bonds? How would you know, like, which one's stronger? S to 3 bond orders, or S to just 1? Which one's stronger? Or which one's longer? Is it the 1 or 3 or 1? 3 single. Okay, so some discrepancies. Okay, can someone tell me why their answer is correct? Eden and Jorge got different answers. How would you know? Length. How do you know which one's longer? There's a trend to it as well. Do we not know? Okay. Okay, actually, because Eden is actually the opposite. That it would be that if there's 1, then it's gonna be longer. Versus 3. 3 is gonna be choppy. It's gonna be like small little bits. 1 is gonna be much longer. And then, yes, and then Jorge, it's always right usually anyways. I saw your smart work score. You're doing fantastic. What about electronegativity scale? Nonpolar. What is that? How do we determine if it's nonpolar? What's the numeric value? I think we went over this last week. So what's the number that's associated? Yes, equal to or lower than 0.4. Exactly. What about polar? Do we know what polar is? Yes, 0.4 to 2, and then ionic is 2, yes, greater than 2. So electrostatic potential energy of an ionic bond between potassium and bromine. We're running out of time, so I'm going to give you the equation for this one because we're just running out of time. So 2.31 times 10 to the negative 19 times Q1 times Q2. And by the way, what does Q stand for again? Does anyone know? This is electrostatic potential, charge exactly. And then D stands for, what is D? Nope, not atomic radii. What does D stand for? I think you're overcomplicating it. Distance, yes. So once you do that, so for this, I'm just going to straight out say that you're just adding multiplying charges, right? So it's 1 times negative 1, because potassium is positive, bromine is negative. It's going to be negative 1 over the distance. What's 157 plus 129? Because you're just adding those, right? 286, exactly. So you have 286, you multiply times this, what will you get? If you guys don't have calculators with you, it's fine. As long as you know how to do the steps, It should be fine. But once you multiply it, what do you get? Yeah, you would. Actually, yeah, I forgot, my bad. But 0.86, again, like, if it's already in the system, like, if it's not PM sometimes, and it's just, like, in nanometers, or just meters, then you'll be fine. Sometimes it's not, sometimes it is. But once you do that, what do you get? If you guys don't have your calculators, it's okay. Yeah, it's okay. But when you get that, here, I'll do it with you guys, because some of you guys don't have calculators. Yes, exactly. So did we all get that? Do we all agree with Eden? We all got that same answer? Or almost that same answer? Did anyone get anything different? Oh, before you guys leave, there's an attendance link every time you guys are here. So I'm gonna put that on the chat as well. But did everyone get that? Or some people just don't have their calculators? Okay, I'm just gonna straight out say that I got the same answer as Eden, except the 10 to the negative 17 is wrong. It's 10 to the negative 19. Okay, so you might want to check your math on that. But other than that, are we all good? Like, we understand how to do this? Raise your hand if you understand. Very good. Okay. So, okay, we all understand. Okay, I'm just gonna let the rest of you guys understand. Okay, that's good. So, yeah, this is a study sheet too. I would suggest knowing this. Again, with the groups, with like the ions, that's how you would know. And then, yeah, that's it. Thank you guys for going to my sessions. I mean, I don't get paid unless you guys go. So thank you for going. And I spend a lot of time making these, so it's really nice to know that you guys come to them and you hopefully learn something from them or enjoy them. So have a great rest of Thursday. I have another review session tomorrow, but if you want like the full review, thank you. If you want the full review, I would say go to the one next week on Thursday, because on